Good evening, everyone. I am Maria Sydney, and our topic for today is about the introduction to linear programming. The topics that we are going to discuss are linear programming problem, problem formulation, a maximization problem, graphical solution procedure, extreme points and the optimal solution, computer solution, a minimization problem, and special cases. Linear programming problem, or linear optimization. It may be defined as the problem of maximizing or minimizing a linear function that is subjected to linear constraints. The constraints may be equalities or inequalities. The optimization problems involve the calculation of profit and loss. Linear programming problems are important class of optimization problems that helps to find the feasible region and optimize the solution in order to have the highest or lowest value of the function. The maximization or minimization of some quantity is the objective in all linear programming problems. Minimization linear programming problems are solved in much the same way as the maximization problem. For the standard minimization linear program, the constraints are on the form of ax plus by greater than or equal to c, as opposed to the form of ax plus by less than or equal to c for the standard maximization problem. In objective function, the objective function should be specified in a quantitative way. The maximization or minimization of some quantity is the objective in all linear programming problems. Minimization linear programming problems are solved in much the same way as the maximization problems. For the standard minimization linear program, the constraints are on the form of ax plus by greater than or equal to c, as opposed to the form of ax plus by less than or equal to c for the standard maximization problem. In the objective function, in a problem, the objective function should be specified in a quantitative way. All the linear programming problems have constraints that limit the degree to which the objective can be pursued. It simply says that the limitation should be expressed in the mathematical form regarding the resource. The third bullet. A feasible solution satisfies all the problem's constraints. In the theory of linear programming, a basic feasible solution is a solution with a minimal set of non-zero variables. Geometrically, each BFS corresponds to a corner of the polyhedron of feasible solutions. If there exists an optimal solution, then there exists an optimal BFS. It is also one that satisfies all defined constraints and requirements. A solution is infeasible when no combination of decision variables values can satisfy the entire set of requirements and constraints. The next one. An optimal solution is a feasible solution that results in the largest possible objective function value when maximizing or smallest when minimizing. An optimal solution to a linear program is a solution which satisfies all constraints with maximum or minimum objective function value. In simpler words, in a linear programming question, we are given an objective function, some constraints, and we have to find minimum or maximum values. The next one. A graphical solution method can be used to solve a linear program with two variables. If both the objective function and the constraints are linear, the problem is referred to as a linear programming problem. A graphical solution means that you draw the vectors with accurately measured magnitude and direction, and then from your drawing measure the magnitude and direction of the resultant vector. The next bullet. Linear functions. Linear functions are functions in which each variable appears in a separate term raised to the first power and is multiplied by a constant, which could be 0. The real valued function whose value is to be either minimized or maximized subject to the constraints. The objective function is needed to solve the optimization problems. An objective function is a linear function represented by z is equals to ax plus by, where our constraints and our variables. The last bullet. Linear constraints are linear functions that are restricted to be less than or equal to, or greater than or equal to a constant. If all the terms of a constraint are of the first order, the constraint is said to be linear. This means that the constant doesn't contain a variable squared, cubed, or raised to any power other than 1. A term divided by a variable or variables multiplied by each other. Extreme points and the optimal solution. The corners or vertices of the feasible region are referred to as the extreme points. An optimal solution to a linear programming problem can be found at an extreme point of the feasible region. When looking for the optimal solution, you do not have to evaluate all feasible solution points. You have to consider only the extreme points of the feasible region. As you can see in the PowerPoint, this one is an example of extreme points. An extreme point is a point that is not part of any interior point or underlying segment in a convex set. It is also defined as a feasible solution, which cannot be written as a convex combination of other feasible solutions. A feasible solution is a solution that can satisfy all constraints in a linear program. So, here's a short video for you to understand more the extreme point.
Welcome to the first video in this linear programming series. In this video, we will graphically solve a basic maximization linear programming problem using the extreme or corner point approach. What we have here is a linear programming or LP model. The x and y in this model are referred to as decision variables. They tell us what quantity to buy, produce, sell, or transport, and so on. The 2x plus 5y here is referred to as the objective function, which we want to maximize. In linear programming, we either maximize or minimize the objective. The next two lines are called constraints. They are restrictions that shape how you attain the objective. Let's call them C1 and C2 for reference purposes. Since we're dealing with real-life objects, we do not expect them to have negative values. So the last line here tells us that both x and y have to be greater or equal to 0. We call them the non-negativity constraints. To solve the model graphically, we begin by finding points that satisfy the constraint lines. For the first constraint, when x equals 0, y equals 8. And when y equals 0, x equals 16. For the second constraint, when x equals 0, y equals 15. And when y equals 0, x equals 9. Now, when drawing the graph, we usually just stay in the first quadrant here, where both x and y are positive because of the non-negativity constraints. So for the first constraint, we have the points 0, 8 and 16, 0. We join those 2 points for the constraint line. We do the same for constraint 2, 0, 15 and 9, 0, and then draw the constraint line. Since these constraints are less than or equal to constraints, they will be satisfied in the region below the lines towards the origin. Therefore, the region satisfying both constraints simultaneously is this one here. It is called the feasible region. That is, any point in this region is a feasible solution. In particular, the optimal or best solution will occur at an extreme point or corner point of the feasible region. These are the corner points for the feasible region. Let's label them 1 to 4. The optimal solution to this linear programming problem will occur in at least one of them. To decide which one is optimal, we will find the coordinates of the point, plug them into the objective function, and then choose the best. At corner point 1, the coordinates are clearly 0, 0. At point 2, 0, 8. at point 4, 9, 0. Now, those are easy to see. For corner point 3, we can see that the coordinates are 6 and 5 by eyeballing, that is, looking at it very closely. But eyeballing is not usually the best way to go when finding the intersection of two lines, especially when manually drawing the graph. So let's see a way to solve the two equations simultaneously to determine the actual coordinates. Here are the lines for the two constraints. Now suppose I choose to eliminate x. Note that the coefficient of x here in C2 is 5. Then I can simply multiply the first equation by 5 to give 5x plus 10y equals 80. And then we can subtract C2 from the new equation. So 5x cancels 5x, 10y minus 3y is 7y, and 80 minus 45 gives 35. And on dividing both sides by 7, we have y equals 5. To now find x, we substitute y equals 5 into any of these three equations. Suppose we choose C1. Then we have x plus 2 times 5 equals 16. That is, x plus 10 equals 16, x equals 16 minus 10, and x equals 6. So the xy coordinates for extreme point 3 are indeed 6 and 5. Next, we determine the optimal solution point by finding the corner point that gives the best value of the objective function. The objective function was to maximize 2x plus 5y. As you can see here, the objective function, or its value, is sometimes represented with z. So now, the xy coordinates at point 1 are 0, 0, and substituting that in the objective function gives 2 times 0 plus 5 times 0, which equals 0. And at point 2, we have 0, 8. So the objective function value is 2 times 0 plus 5 times 8, which equals 40. The coordinates at point 3 are 6 and 5. So z equals 2 times 6 plus 5 times 5, which equals 37. And finally, at point 4 with 9, 0, z equals 2 times 9 plus 5 times 0, which gives 18. So here we have it. Point 2 provides the highest value of the objective function. So the optimal solution occurs at point 2, and it is x equals 0 and y equals 8. And the corresponding objective function value is 40. And that concludes the solution to this LP problem.
Good afternoon mga study buddies. Sa video ito, pag-aaralan natin ang operations research subject. Okay. With this topic, ang ating topic is linear programming problem formulation. So, unahin natin yung maximization model. So, part 1 muna tayo. Okay? So, ano nga ba ang linear programming? So, linear programming is an optimization method which shows how to allocate our limited resources such as material, money, or time, and how to do such an allocation in the best possible way subject to more than one restricting condition. So, gagamitin natin yung mga resources natin to obtain or to attain our objective. Okay? Ano nga ba yung ating objective? Okay. Yung ating objective is either maximize or minimize. Pagdating sa maximization or maximize, pwedeng yan ay revenue, profit, or sales. Sa kabaligtaran, kung ating objective is minimization or minimize, syempre, gusto natin mapababa natin yung ating cost or yung ating man-hour, which is yung man-hour, syempre, mudas yan. So, kailangan mapababa natin yan para bumaba yung ating cost. Okay? Which depend on a finite number of input variables such as ito nga yung ating resources or yung ating limited resources such as materials, money, machine hour, which is tinatawag na constraints. Okay? So, problem formulation tayo. So, normally, yung problem na na-encounter natin is stated verbally or worded problem. Okay? Ang advice is i-convert natin ang ating worded problem into a mathematical program or mathematical equation. Sa ganun, mas mapapadali tayo sa pagsusolve nung worded problem natin. Okay? So, may tatlong step paano gawin. Okay? Una is determine our objective function, which is yung ating objective function is pwedeng minimize or maximize. Second is identify the constraints that we need to identify. So, identify natin yung ating resources, yung ating limited resources, and determine the decision variable that we seek. So, ano ba yung hinahanap or ilan ba yung ipoproduce natin para makuha natin yung ating objective. Either minimize or maximize. Okay? Ito yung isang example ng problem natin, yung Clear Shampoo. So, Gina is the production manager of Clear Shampoo and she wants to determine the production mix that will result in maximum profit. She is able to determine the data necessary for her to make a decision. It will take 5 minutes to mix 1 case of men's shampoo and 10 minutes to mix 1 case of women's shampoo, and she has a total of 100 minutes available for the mixing process per day. It will take 7 minutes to bottle the 1 case of men's shampoo and 7 minutes to bottle 1 case of women's shampoo, and she has a total of 84 minutes available for bottling process per day. It will take 9 minutes to pack 1 case of men's shampoo and 5 minutes to pack 1 case of women's shampoo, and she has a total of 90 minutes available for packing process per day. She will earn 6 pesos for every case of men's shampoo produced and 8 pesos for every case of women's shampoo produced. So, ang haba ng ating worded problem. So, gawin natin yung steps na nire-recommend. Okay, i-follow natin. So, ito nga yun, yung determine the objective function, identify the constraints, and determine the decision variable that we seek. Okay? So, yung una, yung ating objective function or yung ating objective is based sa ating problem. Hinighlight ko na po, nilagyan ko na ng underline para madali nating makita. Pero pag sa mga problem, syempre hindi yan nakaganyan. Okay? For presentation ko, mas madali nating ma-identify. Okay, so for this problem, sabi, pinapahanap or pinadetermine kay Gina yung maximum profit. Okay, so ang ating objective is maximization or max. Okay, number 2, ano ba yung mga constraints natin? Okay, so yung constraints natin is meron tayong tatlong process which are mixing, bottling, and packing. So meron tayong tatlong proseso which is limited yung mga oras na binigay niya. Okay, ito po yung mga oras natin. Merong 5 minutes para sa men's shampoo and 10 minutes para sa women's shampoo with a total of 100 minutes. Pagdating naman sa bottling, merong 7 minutes for men's shampoo and 7 minutes for women's shampoo with a total of 84 minutes. And last process natin or yung last constraints natin, merong 9 minutes for men's shampoo and 5 minutes for women's shampoo with a total of 90 minutes. Okay? So, ating constraints is mixing, bottling, and packing. Okay? Ito yung ating 3 constraints. Okay, so to formulate the mathematical linear programming model for this problem, let x sub 1 is our men's shampoo. Okay, so cases po yan, and x sub 2 is our women's shampoo. Sa ibang book may makikita kayo x2 and ito ay y. Depende po sa inyo yan kung paano nyo or ano yung variable na gagamitin nyo. And let our z is our profit. Okay, so yan po yung mga variable natin. Okay, so x sub 1 cases of men's shampoo produced per day, and x sub 2 is case of women's shampoo produced per day, and yung ating z, yun yung profit natin. So ang tanong kasi is ilan yung ipoproduce nating x sub 1 and x sub 2 para makuha natin or ma-attain natin yung ating maximum profit. Okay, so gumawa ako ng table. Okay, so let x sub 1, so ito yung ating men's shampoo, and yung ating women's shampoo is x sub 2, and yung ating constraints are mixing, bottling, and packing. At ang ating profit z natin. Okay, so based sa problem natin, okay, kukunin natin yung mga value nung available minutes per process or sa constraints natin. Okay, so sa mixing meron daw tayong 5 minutes for men's shampoo and 10 minutes sa ating women's shampoo, with a total of 100 minutes. Okay, ano yung ating magiging symbol or yung sign ng ating equation is less than or equal. Sabi kasi based dun sa ating problem is with a total of. Okay, so hindi sinabi na at least or more than. Okay, so total, so ibig sabihin yung limited o yung restriction na available sa mixing process is 100 minutes per day only, with a combination ng ating 5 minutes sa ating men's shampoo and 10 minutes sa ating women's shampoo. Kumbaga, ilan yung magagawa ng mixing para dito sa limited na 100 minutes, kasi meron siyang mga oras na nilaan na pagmi-mix pagdating sa men's and sa women, pero ang total lang per day na available is 100 minutes. Kumbaga pagkakasyahin natin itong 100 minutes na to kung ilan yung mapoproduce nating men's and women's shampoo. Okay, pagdating naman sa bottling, meron tayong 7 minutes for men's shampoo and 7 minutes for women's shampoo, and a total of 84 minutes. Syempre, with a total, so less than or equal yung ating symbol or yung sign natin. And last natin is 9 minutes for men's shampoo and 5 minutes for women's shampoo, with a total of 90 minutes. Okay? And yung ating profit is 6 pesos and 8 pesos for men's shampoo, equal to max. Okay, so kukunin na natin yung exact value kung magkano yung ating profit. Okay, after natin lagay sa table, okay, yung ating mga values ng bawat constraints, is proceed na tayo. So, ano yung ating objective function? So, our objective function is max z is equal to 6x sub 1 plus 8x sub 2. And yung ating constraints or subject 2, so constraints number 1 muna tayo, yung ating mixing, 5x sub 1 plus 10x sub 2 less than or equal to 100. Ito yung 1 natin, constraints number 1 natin, ito yung mixing. Constraints number 2 natin is 7x sub 1 plus 7x sub 2 less than or equal to 84. Ito yung ating bottling. And last, 9x sub 1 plus 5x sub 2 less than or equal to 90. Ito yung ating packing. And we will have a x sub 1 and x sub 2 is greater than or equal to 0. Ang tawag dito is non-negativity constraints. Okay? Bakit po non-negativity constraints? Whereas, dapat daw yung ating x sub 1 and x sub 2 is 0 or greater than. So, hindi tayo magpuproduce ng negative na product or na men shampoo or nung ating women shampoo. Okay? Totoo naman, di ba? Hindi naman tayo talaga dapat mag-produce ng negative na product. Pwede tayong hindi mag-produce pero hindi negative. Mas mataas sa 0 pero hindi tayo magpo-produce ng negative. Okay? So, ito po siya. Ito yung ating constraints. And ito yung ating non-negativity. Okay? So, try nyong sagutan yung ating problem number 2. Okay? So, para ma-practice kayo. Okay? So, next part natin is solving using graphical solution. Okay? So, that's all. So, thank you.
Everyone, I am Nicole B. Borreros, an NDU graduate under Accountancy Business and Management and currently pursuing Bachelor of Science in Accountancy. I'm the first reporter of Group 2 and we are tasked to report linear programming, computer solutions, and sensitivity analysis. To start off, the application of management science techniques has been frequently credited with increasing the efficiency and productivity of business firms. It has been very helpful in solving problems that confront manager and decision-making processes by developing mathematical models. Now, in the previous chapter, we learned how the linear programming model is being formulated and how it can be solved through a graph representation of the model. This method works almost all different types of problems but gets more difficult to solve when the number of decision variables and constraints increases. So this is where latest technological advances kicks in. The application of mathematical model and computing technology merges to help decision makers solve problems. We will also describe how to use a computed solution result to experiment with a linear programming model to see what effect parameter changes the optimal solution referred to as sensitivity analysis. Now let's get started with our first topic for Chapter 3, Computer Solution. In 1940s, linear programming was first developed. However, during that time, the technologies or inventions are not yet capable to perform these complex problems. They use what we call simplex method, which is a lengthy manual mathematical solution procedure. After 6 decades, computer technology improved and evolved in which it was more used to solve linear programming models. The mathematical steps of the simplex method were simply programmed in pre-written software packages designed for the solution of linear programming problems. It is easy to use and less costly. That's why it was expanded and used by businesses today. Now, simplex method has become less of a focus in teaching of linear programming. However, simplex method is useful in gaining overall understanding of linear programming. As noted, computer solution itself is based on simplex method. Now let me present my PowerPoint presentation about Excel spreadsheets. Before we begin our discussion with Excel spreadsheets, please be informed that Chapter 3 is exclusively focused on computer solution. Also, if you want, you can also bring out your laptops for you to be able to follow the processes in solving linear programming problems. Once again, good day to everyone. Now, let's first tackle what is Excel spreadsheets. Let's start with what Excel spreadsheet is. Excel can be used to solve linear programming problems, although the data input requirements can be more time-consuming and tedious than with a software package like QM for Windows that is specifically designed for the purpose. However, once you already set up one problem in spreadsheet, you can use it as a template for other problems. Next is when you are reporting and presenting. A spreadsheet is a very great way for you to be able to present the problem and its solution in an attractive format. And lastly, a spreadsheet requires that column and row headings for the specific model to be set up and that constraint and objective function formulas be input in their entirety. And now, let's start to set up our Excel spreadsheet. Let's use Beaver Creek Pottery Company example, which was introduced in Chapter 2. Okay, first let's input the data which was also shown in Exhibit 3.1 in our material. The values for bowls and mugs are contained in cells B10 and B11. And for our profit, it is in B12, cell B12. These cells are currently empty or zero because the model has not yet been solved. Okay, the objective function for profit is C4, type it, type equals, and then click the cell C4, and then multiply in Excel spreadsheet. Asterisk is used instead of X. Then click cell B10, then add, then click cell D4, and then multiplied by cell B11. This objective function is embedded in cell B12 shown in the bar or in the formula bar. This formula is essentially the same as z is equal to 4x sub 1 plus 50x sub 2, which was shown in chapter 2 by the group 1. Here, the B10 and B11 represent x sub 1 and x sub 2, while B12 represent z or the profit. Next, the objective function coefficients 40 and 50 are in the cells C4 and D4. Similar formulas for the constraints for labor and clay are embedded in cells E6 and E7. Let's look for E6. In E6, we put the formula equals C6 multiplied by, then click B10 plus, then click cell D6 multiplied, then click B11. So our formula is C6 multiplied by B10 plus D6 multiplied by B11. Now, in E7, we put the formula C7 multiplied by the cell B10. Let's click the B10. Then add D7 multiplied by cell B11. So our formula in E7 is C7 multiplied by B10 plus D7 multiplied by B11. Here, under the constraint, the lesser than or equal to sign in cells F6 and F7 under constraint are for cosmetic purposes only, meaning they have no real effect. In H7 or leftover, under the leftover heading, the formula we input is equals to G7 minus E7, and in H6, we input G6 minus E6. To solve this problem, first click on the Data tab on the toolbar at the top of the screen, and then click on Solver on the far right side of the Data toolbar. If you can't find it, you can always use the search bar. The Windows Solver parameters will appear as shown in Exhibit 3.2 in our material. Initially, all the windows on this screen are blank, and we must input the objective function cell, the cells presenting the decision variables, and the cells that make up the model constraints. Now, when inputting the solver parameters, we first set objective, which is, in this case, B12 for example, since our profit is embedded in cell B12. Next, we indicate that we want to maximize the objective by clicking on Max. we achieve our objective by changing cells B10 and B11, which represent our model decision variable. It means that all the cells between B10 and B11 are inclusive. Next, we input our model constraints by clicking on Add, which will access the screen to another command just like what is shown in Exhibit 3.3 in our material. The cell E6 contains the constraint formula for labor, whereas cell G6 contains the labor hours available. We continue to add constraints until the model is complete. So E6, then here we put G6 and click on Add, then E7, then G7. Because E6 is to E7, lesser than is equal to G6 is to G7, which means that the constraints in cells E6 and E7 are less than or equal to the values in cells G6 and G7 respectively. It is also not necessary to put or to input the non-negativity constraints for our decision variables. B10 is to B11 is greater or equal to 0. This can be done in the solver parameter screen, Exhibit 3.2 or Exhibit 3.2. Now, let's click on OK on the Add Constraint window after all constraints have been added. This will return us to the solver parameter screen. On the solver parameter screen, check this where it says Make Unconstrained Variables Non-Negative, and this, let's select this where it says Select a Solving Method. And then we select Simplex LP. This will ensure that the solver uses simplex procedure to solve the model and not some other numeric method. Once the complete model is input, click on Solve at the bottom of the solver parameter screen. First, a screen will appear titled Solver Results, which will provide you with the opportunity to select the reports you want, and then when you click on OK, the solution screen shown in Exhibit 3.4 will appear. If there had been any extra or slack left over for labor or clay, it would have appeared in column H on our spreadsheet under the heading Left Over. In this case, there are no slack resources left over.
Computer solutions. First bullet. Computer programs designed to solve linear programming problems and now widely available. Second bullet. Most large linear programming problems can be solved within just few minutes of computer time. Third bullet. Small linear programming problems usually require only a few seconds. And last bullet. Linear programming solvers are now part of many spreadsheets packages such as Microsoft Excel. Interpretation of computer output. In this chapter, we will discuss the following output. First bullet, objective function value. Second bullet, values of the decision variables. Third bullet, reduced cost. Last bullet, slacks or surplus. In the next chapter, we will discuss how an optimal solution is affected by change in a coefficient of the objective function. And last bullet, the right hand side value of constraint. Example number 1, spreadsheet solution. This is a partial spreadsheet solution showing problem data. We have LSH coefficients, variable 1 and variable 2, RHS values, and constraint constraints number 1, constraints number 2, and constraints number 3, and objective function coefficient. LSH coefficient variable 1 is 1. 2, constraints number 1. LSH coefficients variable 1, 2 in constraints number 2. And LSH coefficients 1 in constraints number 3 is 1. And LSH coefficient 5 is for objective function coefficient. LSH coefficient variable 2, 0 is for constraint number 1. LSH coefficients variable 2 is 3 for constraints number 2. LSH coefficients variable 2 is 1 for constraints number 3. And LSH coefficients variable 2 is 7 for objective function coefficient. RSH values is 6 for constraints number 1. As is RHS values 19 is for constraint number 2. RSH values 8 for constraints number 3. Example 1. Spreadsheet solution. This is a partial spreadsheet showing solution. Optimal decision variable values. Variable 1 is 5.0 and variable 2 is 3.0. Maximize objective function is 46.0. Constraint number 1, constraint number 2, and constraint number 3. Amount used 5, 19, 18. And RHS limits is 6, 19, and 8. Constraint number 1, amount used is 5 is less than or equal than 6 RHS limits. Constraint number 2 is 19 less than or equal 19 RHS limits. And constraint number 3, amount used 8 less than or equal 8 RHS limits. Example 1. Spreadsheet solution. Interpretation of computer output. We see from the previous slide that objective function value is equals to 46. Decision variable number 1 is equals to 5. Decision variable number 2 is equals to 3. Slack in constraint number 1 is equal to 1. Slack in constraint number 2 is equal to 0. Slack in constraint number 3 is equal to 0. Reduced cost. The reduced cost for a decision variable with a positive value is 0. Example 1. Spreadsheet solution. This is the spreadsheet solution of reduced cost. Next slide.
Maximization problem is just that the operation or the symbol used to compute for the value of exab 1 and exab 2 intercepts. Kung mapapansin nyo, in maximization problem, ang ginagamit doon is less than or equal. Okay? And samantala naman dito sa minimization problem, ang ginagamit naman ditong symbol is greater than or equal. So, let's start. Okay? So, ang i-minimize naman natin dito is yung 5 exab 1 plus 2 exab 2 using the constraint given in this slide. Okay? So, continue. So, example tayo. So, constraint number 1, when exab 1 is 0, then exab 2 is 2. When exab 2 is 0, then exab 1 is 5. Connect 5, 0 and 0, 2. The greater than side is above this line. So, kung maaalala nyo sa maximization problem, in able to get the value of exab 1 or exab 2, we just only change the value of any of these 2 into 0. Okay, and able to get the value of exab 1 or the exab 2. Okay? So, ganun lang din ang gagawin natin dito sa minimization problem. Okay? So, constraint number 2. When exab 2 is 0, then exab 1 is 3, but setting exab 1 to 0 will yield exab 2 to negative 12, which is not on the graph. Thus, to get a second point on this line, set x sub 1 to any number larger than 3 and solve for x sub 2 when x sub 1 is 5, then x sub 2 is 8. Connect 3, 0 and 5, 8. The greater than side is to the right. Okay? So next, constraint number 3, when x sub 1 is 0, then x sub 2 is 4. When x sub 2 is 0, then x sub 1 is 4. Connect 4, 0 and 0, 4. The greater than side is above this line. So, ito na yung graph na pinagsasabi natin kanina. So, halos wala naman itong pinagkaiba kumpara sa maximization problem dahil i-connect lang din naman natin yung mga value na nabanggit natin kanina from x sub 1 to x sub 2 and able to get the feasible region and able to get the objective function and the optimal solution. Okay? So next, graph the objective function. So sabi dito, set the objective function equal to an arbitrary constant. Halimbawa, 20. Okay? For 5x sub 1 plus 2x sub 2 is equals to 20. So itong 20 na to, ito lang naman yung ito yung assumed value lang. Okay? So when x sub 1 is 0, then x sub 2 is 10. When x sub 2 is 0, then x sub 1 is 4. Connect 4, 0 and 0, 10. Moving on, move the objective function line toward optimality. Okay? Move it in the direction which lowers its value because it is a minimization problem. Okay? Since, sabi dito, we are minimizing until it touches the last point of the feasible region determined by the last two constraints. Okay? So, in the next graph, makikita natin yung mga sinasabi dito. Okay? Okay, so here's the graph. Since minimizing a problem ang ginagawa natin dito, pababa naman ang kanyang tulak hanggang sa ma-meet ng objective function line which is the 5x sub 1 plus 2x sub 2, yung extreme points or yung optimal solution or yung binding points of the constraints. Okay, so ganun lang kadaling intindihin to. Okay, so next, solve for the extreme point at the intersection of the two binding constraints. Okay? So, for x sub 1 minus x sub 2 is equals to 12, x sub 1 plus x sub 2 is equals to 4. Adding these two equations gives 5x sub 1 is equals to 16 or x sub 1 is equals to 16 over 5. Substituting this into x sub 1 plus x sub 2 is equals to 4 gives x sub 2 is equals to 4 over 5. Okay? Solve for the optimal value of the objective function. Same lang to nung ginawa natin doon sa maximization problem na sinubstitute lang natin yung value ng x sub 1 and then yung value ng x sub 2. Okay, so ganun lang dito. So, solve for z is equals to 5x sub 1 plus 2x sub 2 is equals to 5 multiplied by 16 over 5 plus 2 multiplied by 4 over 5 is equals to 88 over 5. Thus, the optimal solution is x sub 1, 16 over 5, then x sub 2 is 4 over 5. Okay? Next. So, ito na yung graph sa optimal solution. Okay, after na makuha natin yung value of ng x sub 1 and x sub 2. Okay, so ganun lang kadali yun. So ito naman yung mga spreadsheet solution. Okay, so slide 1, partial spreadsheet showing problem data. Slide 2, partial spreadsheet showing formulas. And slide 3, partial spreadsheet showing solution. Okay. Next, feasible region. Okay, so halos familiar na sa inyo tong salitang ito dahil nakita na natin ito sa maximization a problem and sa minimization a problem. So, pakibasa nyo lang itong slide na to dahil nandito na yung pinaka-explanation. Okay, so next. So, good morning sir. In this slide, we are able to understand what is the maximization problem, how to compute the maximum value of the objective function, and how to put it on the graph. Okay, so magsimula na tayo. So, what is maximization problem? So, the maximization problem in linear programming in which we seek to maximize an objective function. Okay, meaning to find a maximum value of the given data or variable. Okay, na ilalagay natin sa graph. Okay? So, in knowing what is the maximization problem, there are three components used in every optimization problem. These are the objective function, the constraints, and the decision variable. So, what is the objective function? Objective function is the real valued function whose value is to be either minimized or maximized subject to the constraints. It has three variables. So, for example, ang gagamitin ng variables is x plus y is equal to z. So, okay? So, that will be the objective function that need to maximize. Okay? So next, the constraints. What is constraints? So it is the linear inequalities or equations on the variables of linear programming problem. It has two variables. Ito naman yung gagamitin natin in able to maximize the objective function. Okay? So third, decision variables. Ito naman yung mga unknown quantities that are expected to estimate as an output of the linear programming solution. So, mas ma-appreciate natin itong tatlong components na to once na magsosolve tayo ng problem. Okay? Okay, so tapos natin malaman yung objective functions and what are the constraints. Now, ipa-plot naman natin siya o ilalagay naman natin siya sa graph. Okay, so for example, number 1, graphical solution, constraint number 1. Okay, since walang ibang variable ang naka-indicate to compute the x sub 2 intercept, just simply plot the x sub 1 is less than or equal to 6 on the x sub 1 intercept. So ayan. Okay? So punta naman tayo sa constraint number 2. So able to compute the value of x sub 1, which is the 9.5, just simply change the value of x sub 2 into 0. So the formula or the solution is 2x sub 1 plus 3 multiplied by 0 is less than or equal to 19. Ang magiging kalabasan nito is 2x sub 1 is less than or equal to 19. Okay? Because 3 multiplied by 0 is 0. So to compute the value of x sub 1, we need to divide it by 2. Okay? So 2x sub 1 divided by 2 is x sub 1. So 19 divided by 2 is 9.5. So the value of the x sub 1 intercept is 9.5. So ayun. Okay? So ganun din sa x sub 2. So we change the value of x sub 1 to 0. So the solution is 2 multiplied by 0 plus 3x sub 2 is less than or equal to 19. So compute for the x sub 2, we need to divide it by 3. So 3x sub 2 divided by 3 is x sub 2. 19 divided by 3 is 6 and 1/3. So ayun. Okay, just simply plot that. Okay? So here in combined constraint graph, we just simply plot all the constraints given above. Andyan yung x sub 1 plus x sub 2, 2x sub 1 plus 3x sub 2 is less than or equal to 19, and the x sub 1 is less than or equal to 6. Okay, so napakadali lang naman. Now, after we identify the different maximum value that are plot in x sub 1 and x sub 2 intercept, pagsasama-samahin natin sila into one graph, enable to find the area where all the graphs overlap. So here mula sa x sub 2 intercept, which is 6 and 1/3, and sa x sub 1 intercept of 6, these are the region which satisfies all the restrictions or a set of points that satisfy every inequality in a set of inequalities. Okay? To get the objective function, gagawa tayo ng column. Okay? 3 columns. X sub 1, x sub 2, and any variable na gusto mo. Kung halimbawa, y. So, ilalagay natin under the x sub 1 is yung 9.5. X sub 2 is 0. X sub 1, 0. X sub 2, 6 and 1/3. And x sub 1 is 5. And x sub 2 is 3. Okay? Okay. So in the objective function line, we will just simply multiply the two coefficients, which is 5 and 7 is equals to 35. Okay? So paano naman ito i-plot itong linya na ito? So if the value of x sub 1 is 0, then the value of x sub 2 is 5. So kung makikita nyo dito, ayun. Okay? If the value of x sub 2 is 0, then the value of x sub 1 is 7. Kung makikita nyo rin, ayun, nakalinya. Then, connect mo lang silang dalawa. So, it is used to determine the best extreme point. So, we will move it up because it is a maximization process. Enable to find the optimal solution. Okay? So, optimal solution, pag-aaralan natin yan sa next slide. Now, sa optimal solution, as you can see, our objective function is 5x sub 1 plus 7x sub 2 is equals to 46. And our optimal solution is x sub 1 is equals to 5, x sub 2 is equals to 3. So, paano na-compute yung optimal solution of x sub 1 and x sub 2? Okay? So, magsimula tayo sa x sub 2. So, to compute, x sub 2 is equals to 3. Using the constraints number 2 of 2x sub 1 and plus 3x sub 2 is less than or equal to 19, we will eliminate the x sub 1 using the given data in constraint number 1, which is x sub 1 plus x sub 2 is less than or equal to 8 to get the value of x sub 2 of 3. Okay, so to compute, x sub 1 plus x sub 2 is less than or equal to 8. Multiply by negative 2. Bakit? To eliminate the x sub 1 and to get the x sub 2, the value of x sub 2. So, the solution, negative 2 times x sub 1 is negative 2x sub 1. Negative 2 times positive x sub 2 is negative x sub 2 is less than or equal to 2. Negative 2 multiplied by 8 is negative 16. So, here, we will deduct it to 2x sub 1 plus 3x sub 2 is less than or equal to 19. So, negative 2x sub 1 plus 2x sub 1 is equals to 0. And then, negative 2x sub 2 plus 3x sub 2 is equals to x sub 2. Okay? Then, negative 16 plus 19 is equals to 3. Okay? So, the value of x sub 2 is equals to 3. Okay? So, to compute naman, the x sub 1 is equals to 5. So, ganun pa rin. Gagamitin natin yung data na nasa constraint number 2. Just change the value of x sub 2 of 3. So, to compute, x sub 1 plus 3, okay, is less than or equal to 8. Okay? And then, x sub 1, yung 3 transpose sa kabila, magiging negative. Then, kalalabasan is 8 minus 3. Okay? Then, ang value ng x sub 1 is 5. Okay? Ganyan lang mag-compute ng optimal solution.
Okay, now let us talk about this what we call special cases. Under the first bullet, alternative optimal solution, in the graphical method, if the objective function line is parallel to the boundary constraint in the direction of optimization, there are alternative optimal solution, with all points on the line segments being optimal. Okay, next bullet is infeasibility. A linear function which is over-constrained so that no point satisfies all the constraints is said to be infeasible. Then the last one is unboundedness. So there are few examples on the next slide.
Welcome to this tutorial on special cases encountered while solving linear programming problems. The special cases we'll discuss include alternative optimal solutions, infeasibility, unboundedness, and redundancy. Let's begin with alternate optimal solutions. Consider this linear programming problem and its graph. Here is an instance of the objective function line. Since this is a maximization problem, moving this line shows that the optimal solution occurs at these two extreme points. That is, more than one optimal solution exists. We refer to these as alternative or multiple optimal solutions. Generally, this situation occurs when the objective function line is parallel to a binding constraint. Note that the objective function and the first constraint line have the same slope, so they are parallel. That is why the objective function line coincides with the constraint line here. In fact, not only these 2 points are optimal solutions, every single point between them on the line is also optimal. There's nothing wrong with alternative optimal solutions. They offer the benefit of different combinations of the decision variables that produce the same optimal profit or cost. The next special case is infeasibility. Consider this linear programming problem and its graph. The first constraint is a less than constraint and is satisfied in the region here towards the origin, while the second constraint is a greater than constraint satisfied here away from the origin. As you can see, there is no region satisfying both constraints at the same time. So we say there is no feasible solution or no feasible region, or we have a condition referred to as infeasibility. The next special case is unboundedness. This is a situation that applies only to maximization problems. Because all these 3 constraints are greater than constraints, the feasible region is this region shaded here. Since this is a maximization problem and the feasible region is open-ended, we can move the objective function line infinitely without reaching the end of the feasible region. As a result, the situation is called unboundedness. It suggests that we can make unlimited profit, which is impractical. It is usually due to a formulation error or by assuming a resource could be unlimited in supply. The last special case we'll discuss here is redundancy. Suppose you're applying to enter a contest where applicants have to be at least 15 years old. If X represents age, then we have X greater or equal to 15. Suppose also that applicants must have a valid driver's license. If the minimum licensing age is 16, then applicants must be at least 16 years old, and we have X greater or equal to 16. So we call this first constraint redundant because its effect has been overshadowed by the second constraint. Now consider this minimization problem. Here is a graph showing its constraint lines. Since these are all greater than constraints, here is the feasible region. As you can see here, constraint 3 line does not touch the feasible region at all. Therefore, it is redundant. So a redundant constraint is one that does not affect the feasible region. In essence, we could remove a redundant constraint without changing the feasible region or optimal solution. And that concludes this video on special cases in solving linear programming problems. Thank you for watching.